Happy Thursday. We're done with integrals. For the most part. We're still going to see integrals here and there, but they're not going to be the main focus anymore. We're starting our study of infinite series. We do so by looking at sequences. For lack of a better definition, right, so we're just going to kind of broadly define it. Sequence is a list of numbers. Right. Some sequences can be represented as a function. And typically, the independent variable of the function has a domain of integers. Other sequences do not have such a function. We also have sequences that are recursively defined. Right. Most famous recursively defined sequence is the Fibonacci sequence. Right, where you have 1, 1, and then each term in the sequence is the sum of the previous two. Ultimately, what we want to do is look at convergence of sequences. What does it mean for a sequence to converge? And then how do we find what it converges to? Again, not every sequence will converge. Let's start by finding an explicit formula. You first want to decide where are we going to start? General convention is we start with n equals 1. But that doesn't mean you have to. I'm going to. So I'm going to say the first term is the n equals 1 term, second is the n equals 2, third is n equals 3, so on and so forth. Once you have your starting point, now we can try and derive a formula. When n equals 1, we have a half. When n equals 2, we have a quarter. N equals 3, we have a sixth. N equals 4, we have an eighth. Well, they definitely have one thing in common. Numerator is always 1. So there's a start. What do we notice about the terms in the denominator? They're all even. Specifically, it's every even term. How do you represent an even number? What is it? Oh, I see. You're trying to define it recursively. No, don't do that for this. Right? Even numbers are just 2 times an integer. So 1 over 2n. Okay? And that is for n greater than or equal to 1. Right? And the reason we don't want a recursive formula is because it specifically says find a formula for the nth term. With this, I can then say, okay, what is the 223rd term in the sequence? It'll just be 1 over 2 times 223. Right, so you can find every single term in the sequence. So the sequence: a half, 2/3, 3/4, 4/5, so on and so forth. Again, let's just start with n equals 1. So first term would be 1/2, second term 2/3, third term 3/4, fourth term 4/5, so on and so forth.
You're starting at 1. Could you just do n over n plus 1?
One, negative a half, a third, negative a quarter, a fifth, negative a sixth, so on and so forth. Well, we should notice immediately it's alternating. Right. Specifically, starting with 1, all the odd terms in the sequence are positive. All of the even terms in the sequence are negative. Well, the easiest way to represent alternating is -1 to some power. Well, -1 to an odd would be negative, right? -1 to an even would be positive. Since we want odd terms to be positive, we're going to want our exponent for odd terms to be even. And then all of the even terms are going to want an odd exponent. n+1 or n-1, either one would work. That's going to be times something. Point 0.9, 0.99, 0.999, 0.9999, so on and so forth.
One minus 0.1 to the n.
0.1 to the n?
Yes.
Yeah, that'll work. It's not how I would write it. It's typically not how you've see it written, but yes. That's typically how you would see it written. Of course, they're the exact same thing, right? One, 0, -1, 0, 1, so on and so forth.
You're not allowed to use modulus, right?
No. Well, even if you use the mod, you wouldn't get negatives. It would be clever. Square roots don't give you negatives. Is it alternating? Is it? No, it's not an alternating. To be alternating, every other term would be negative. Those zeros really throw a wrench into it. There's a huge clue. All of the terms are between -1 and +1. What function will always give you a value between plus and -1? There's
Functions.
specifically, there's only two of them. Sine and cosine. We want n equals 1 to give us 1. N equals 2 to give us 0. N equals 3 to give us -1. N equals 4 to give us 0. So that's going to immediately pick either sine or cosine. Sine of what? Just n? Sine of 1. That's not 1. Sine of n pi over 2. And remember, for all these, it is understood that n is always an integer. You would never get zeros out of that.
Is there another?
Cosine is 0 at odd multiples of pi over 2.
Is there another way without using trig functions to represent this series
Sequence.
sequence?
None that I can see. So none that pop right out to me. Two 9/4, 64 over 27, 625 over 256, so on and so forth.
And the next number increasing by And how. Two to one, three. Three.
Where's the 2 squared, 3 cubed? What about the numerator?
I think it would be n plus 1 to the n over n to the n.
Which can be simplified. N plus 1 over n all raised to the n. Right? 2 over 1 raised to the first power, right? 9/4 is 3/2 raised to the second. 64 over 27 is 4/3 raised to the third. 625 over 256, 5 over 4. Right, all raised to the fifth power. Fourth power. So on and so forth. Right. But then you could get some sequences that, as I said, do not have a formula. To load something up real quick. Well, it's not E. There is no explicit formula because E is an irrational number. Right, so there is no explicit formula for the nth digit of E. But the digits still form a sequence. Same thing with pi. Digits of pi form a sequence. So let's talk about when a sequence converges. So we say that a sequence, in this case, I'm going to represent each term a sub n, converges to a value L if for every epsilon greater than 0, there exists some big N greater than 0. Such that the absolute value of a sub n minus L is less than epsilon for every little n greater than that big N. You can also see it sometimes written greater than equal to. They're the same thing. Right? The idea is the same. There is some point in the sequence at which every term after that falls within that epsilon band of L.
So epsilon usually do.
No, it's for every epsilon greater than 0. By the way, this should look familiar, at least for 2 of you.
How limits are defined? Oh, sort of.
More specifically, it's a certain type of limit,
Limits. Epsilon delta.
not ad infinity.
Yes.
Wait, I'm sorry, yes, ad infinity. I was thinking of the other infinity, when it equals infinity. This is called an epsilon n definition. And we'll write the limit as n approaches infinity of a sub n is equal to L. And here's the good news. Isn't a sub n a function of n? That means you just take the limit the same way we did in Calc 1. Here's the bad news. That means all of the rules of Calc 1 apply, including, dare I say it, squeeze theorem. But L'Hopital's rule would also apply. Problem with L'Hopital's rules, as we're going to see, a lot of the time we're going to have factorials. What's the derivative of x factorial? I'd actually have to look it up because I don't know if such a derivative even exists. What would a sub n converge to here? Right, the terms converge to 0. What about b sub n? What does that converge to? Hmm? 1. What about c sub n? Zero. We actually take a look. Right, yes, it's alternating, but notice that the magnitude is getting closer to 0. So yes, the terms actually are stabilizing out to 0. What about d sub n? Converges to 1. What about e sub n? It does not converge. And it's going to keep doing that. What about f?
Something related to E.
What do you mean related to E?
As in, I've seen some similar limits where they end up doing L'Hopital's rule and get natural logs used, and the result usually.
Well, they use natural logs first and
Well,
then
yeah,
wind up using
but then
L'Hopital.
the-
This one is actually a beast to do by hand. I've tried. This actually converges to E. How do I know that? I'm so glad you asked. I just use a calculator to calculate the limit. This is a bit of a beast to do by hand. Obviously, G sub n does not converge. So what is this limit? How'd you get it?
Because you're only really worried about the greatest power. That just gives you 5n squared over 3n squared, and then 2n squared simultaneously.
Because it's rational. This is where function analysis is going to come in handy. Knowing how functions behave will make finding these limits so much easier. What's this limit? That limit's just infinity. Which, by the way, means the sequence does not converge, right? That sequence diverges. What's that limit? Just 0.
Zero.
N to the 4th plus 1 increases a lot quicker than natural log of n. Since it's in the denominator, that means the limit's 0. That limit is also 0. That is easily done using squeeze theorem. But if you just look at it, you know sign's going to alternate between +1 and -1. And the denominator is going to keep increasing. That's going to eventually just be 0.
Doesn't have any.
That's what I think. I just want to double check.
It's periodic.
Now, sometimes we're just concerned with whether the bloody thing converges. We don't care what it converges to. Show the sequence defined by S sub n equals 2n minus 1 double factorial all over 2n double factorial is convergent. Right. Well, if we tried to do this, actually, we could do that. I can do that. No, I can't. Never mind. That's going to be a beast. So 2n minus 1 double factorial. Who's familiar with factorial? Right, what would factorial be?
If your number's n, it's n times n minus one, etc. until one.
Right? It's the product of those n integers. Double factorial. It just skips every other integer. So it's the product of every other integer. You may also see it written the other way, 1 times 3 times 5 times so on and so forth up to times 2n minus 1. Same thing. There are two things that are going to be helpful. The idea of monotonicity and the idea of bounded. Because there's a very useful result that says all monotone bounded sequences converge. If we can show that this sequence is monotone, either increasing or decreasing, and is bounded, then we're done. It converges automatically. By the way, the monotone only has to be after a certain point. Right, so as long as it's monotone after a certain point and bounded after a certain point, it'll converge. Right, again, because it's going to infinity, right? So we can have, I don't know, the first 100 million terms doing whatever the hell they want. As long as after that, it's bounded and monotone, it converges. And to rewrite S sub n, the 1 times 3 times 5 times so on and so forth up to times 2n minus 1 all over 2 times 4 times 6 times so on and so forth up to times 2n. Wasn't that a half times 3/4 times 5/6 times, what would it be, 7/8 times so on and so forth up through times 2n minus 1 over 2n. Well, 1/2 is less than 1. 3/4 is less than 1. 5/6 is less than 1. Specifically, everything is less than 1. So you're taking a bunch of numbers less than 1 and multiplying them together. The result is a value less than 1. That means 1 serves as an upper bound for the sequence. In fact, it might even be the supremum. The least upper bound. By definition, this has to be greater than 0. That's just by definition of double factorial. 0 serves as a lower bound. Hence, S sub n is a bounded sequence. It's bounded both above and below. Now we just have to verify that it is monotonic. Let's take a look at S sub n plus 1. Right? If it is increasing, then this would be larger than S sub n. If it is decreasing, this will be less than S sub n. By definition, this is going to give us 2n plus 1 double factorial over 2n plus 2 double factorial. Using properties of factorials, two n plus 1 double factorial will be 2n plus 1 times 2n minus 1 double factorial. 2n plus 2 double factorial would just be 2n plus 2 times 2n double factorial. Isn't that S sub n? So we get 2n plus 1 over 2n plus 2 times S sub n. So that is Sn plus 1. That term's less than 1, isn't it? Which means Sn plus 1 is less than S sub n. This means that S sub n is monotonic decreasing. This means that S sub n is a bounded monotonic sequence. So by the monotone convergence theorem, it converges. What does it converge to? Don't know. Just know it converges. Strictly increasing or strictly decreasing?
Has to be convergent. That's true.
Yes. So if it's bounded and monotonic, then it converges. Specifically in this case, we don't care if it's bounded above. Since it's monotonic decreasing and it's bounded below by 0, it has to converge, right? Because it's always decreasing and we know it's never going to drop below 0. Hence, it has to converge. Specifically, it's going to converge to some value between 0 and 1. If I had to take a guess, I would assume this converges to 0. Factorial, n factorial, or I'll use a number. 8 factorial. 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. So factorial is just the product of those n positive integers. Double factorial is the same thing, it just skips every other integer. You also have a triple factorial, which would be it skips every 2, right, so on and so forth. And we're going to be seeing factorials a lot. I want to show that this sequence is divergent. Right. Keep in mind, the monotone convergence theorem is only one way. Right. It says all bounded monotonic sequences converge. It does not say all convergent sequences are monotonic bounded. Right. So just showing that this is not monotonic or not bounded is not enough. Right. Perfect example of that would be C sub n. C sub n is not monotonic, but it does converge. So if we just say a sub n is n factorial over 2 to the n, an plus 1, n plus 1 factorial over 2 to the n plus 1. Right, that's n plus 1 times n factorial over 2 times 2 to the n. This may not work out the way I want it to. This is not working out the way I want it to. Because this shows it's monotonic decreasing after a certain point, specifically for n greater than 2.
It doesn't. Because it's not bounded, so it's increasing.
I forgot about the one result. Pretty sure there is a result that says all convergent sequences are bounded. I actually don't need to show that. I was gonna go, oh, it's not bounded above and it's increasing. So it can't converge, but this is not increasing. So that backfired.
It is increasing.
It's not. This is decreasing after 2.
But think about like a large value of n.
Right.
You add n plus 1, well, you multiply the numerator by n plus 1 and the denominator by 2. So you're multiplying by a positive number.
Oh, wait, I'm sorry. I was thinking of 2 over n plus 1. Yeah, no, you're right. You're right. It'd be 3 halves, then 4 over 2. Yeah, perfect. So as long as n is greater than 2, this is increasing. Perfect. So we know that after 2, the sequence will just increase. The terms increase. Perfect. That should be 2 to the n. Right. N factorial is 1 times 2 times 3 times 4 times 5 times 6 times so on and so forth up through times n. Obviously, 2 to the n is just 2 times itself n times. No, it's just whatever number n happens to be. It's n times all the positive integers less than it. Right, so notice if n was 2, these would just go away, right? It would just be a half. Well, isn't that greater than n over 2. Actually, I think I can go even lower. I think I can do greater than or equal to 3. Can I? No, I can't. No. Because that'll be 3/4. Yeah, it has to be greater than 4. This means there's no upper bound. Right? After n equals 4, it just, the terms just keep getting larger and larger and larger.
Does n over 2 come in as that reference point?
Oh, just the fact that n is some integer, right? So obviously n over 2 keeps getting larger as n gets larger, right? Again, for greater than 4, which means that my term will always be larger than that, but this is increasing without bound. So we have a term that's larger than a term that's increasing without bound. So it has no upper bound. So it's increasing with no upper bound. Hence, it has to diverge. Right, in fact, with some understanding of how the functions work, you can actually just look at that limit and see it's infinity. N factorial increases a lot faster than 2 to the n. I think 10 factorial already over 1,000,000. 100 factorial versus 2 to the 100. 100 factorial, you can't even calculate on the calculator. It gives you an overflow error. Yeah, 10 factorial is already 3.6 million. That 100 factorial gives me an overflow. Oh my god, it doesn't. I love this calculator. However, it did not give it to me in scientific notation, so I have no idea how large it is, and I'm not scrolling through all those numbers. So let's fix that. Oi, that's not scientific notation. You lied to me. I don't know, it's some insanely large number. I'm gonna push this until I get an overflow error. Oh, 1,000 factorial just gives me 1,000 factorial. Nice. If I do control enter. It just gave me infinity. Ah, there's my scientific notation. 100 factorial is about 9.3 times 10 to the 157. Mind you, a Google is 10 to the 100. So this is larger than a Google. Imagine sitting there and having to calculate 100 factorial by hand. So let the limit as n approaches infinity of S sub n equal L, which is the same as the limit as n approaches infinity of U sub n. So in other words, Sn and Un converge to the same value. Let's also suppose there is an integer m such that Sn is less than or equal to Tn, less than or equal to Un for all n greater than or equal to m. We're going to prove that T sub n also converges to L. In other words, we're proving the squeeze theorem. Let epsilon greater than 0 be given. Then there has to exist an integer n greater than or equal to m such that the absolute value of S sub n minus L is less than epsilon over 4, and the absolute value of U sub n minus L is less than epsilon over 4. Why I wrote that in? May that might be the right level n greater than or equal to big N. For little n larger than big N, This would mean that little n is also larger than little m. So we know that Sn is less than or equal to Tn less than or equal to Un. No, did that backwards. Tn minus Sn less than or equal to Un minus Sn. However, if we take a look at the absolute value of U sub n minus S sub n, just add 0, so add and subtract L. So Un minus L plus L minus Sn. By the triangular inequality, that would be less than or equal to the absolute value of U sub n minus L plus the absolute value of L minus S sub n. But because we're in absolute values, you can flip the order of subtraction. So L minus Sn is the same as Sn minus L in absolute values. But each of those absolute values are less than epsilon over 4. This means that the absolute value of Tn minus Sn is less than epsilon over 2. All right, so play the same game. Going to add and subtract Sn within the Tn minus L. Triangle inequality. First term, less than epsilon over 2. Second term is less than epsilon over 4. Which is 3 epsilon over 4, which is definitely less than epsilon. which is the definition of the limit of T sub n being L. Welcome to abstract mathematical thinking. The fun's just getting started. Any questions? That might make a good test question. Just make the test 5 proofs. I mean, in a sense, it is going to be 5 proofs, right? Because with series, you have to prove your answer. Here's a hint. Write out the first few terms of the sequence.